Hello dear friends, welcome back to the tetrahedron chemistry classes. So guys, in today's class I am going to discuss a very important topic which deals with the metallic bonding, right? So the name of the topic is the band theory of the solids, you can say, or you can say it molecular orbital theory of the metals, right? Basically it is a quantum mechanical treatment of the metallic bond. But we will not discuss the quantum chemistry involved in this particular concept. We will only see the qualitative aspect of this quantum mechanical treatment of the metallic bond, right? So it is very important for the chemistry people, right? If you are from physics background, or say you are doing your engineering, then you need to know little more about the band theory of the solids, right? Then whatever I will discuss here, actually you will need more than that if you are from the physics background or the electronics background, right? But for the chemistry people, this would be sufficient, right? So why? See, first of all, we will see why the name of the theory is the band theory, how the band originates, right? So for this, I'll take the example of this very basic molecule. This is the molecular orbital diagram of the lithium. Okay, this is the molecular orbital diagram of the lithium. However, there are certain problems with this diagram, because energy in that case is going up, which is not showing. This diagram is the downloaded diagram. This is the atomic orbital. This is the lithium atom. This is again the lithium atom, and here is the diatomic lithium molecule, right? And these are the atomic orbitals, 1s2 of the lithium, and this is 2s1 of the lithium, right? One electron containing one electron, and this one is containing two electrons. Similarly, on the right hand side, you are having another lithium atom, and these are the two s orbitals of the lithium atoms, and we are going to form this lithium molecule. And in the light of the molecular orbital theory, you can see we have developed the molecular orbitals, and this is your BMO bonding molecular orbital, and this is your ABMO anti-bonding molecular orbitals, right? So likewise here again you are having the BMO and ABMO. I am not discussing the basics of the molecular orbital theory. However, I haven't uploaded any video about the molecular orbital theory of the diatomic molecules. Very soon I will upload that lecture as well, but for now I am assuming that you are well aware about the molecular orbital theory of the diatomics, right? And since we are talking about the metals, and you know the metals generally have the tendency to conduct the electricity, whether it can conduct the thermal conductivity, it may have the thermal conductivity, it may have the electrical conductivity. And you know, in any type of the conduction, only valence electrons are important. And I hope you know what are the valence electrons. So for example, this is my lithium having the atomic number of 3. If you write the electronic configuration, it is 1s2 and it is 2s1. Okay, so this 2s1 is the valence electron, right? And this valence electron is responsible for the thermal conductivity. Okay, please remember this point. I am writing thermal conductivity, and as well as this electron is also responsible for the electrical conductivity. Okay, these two conductivities are possible only due to the presence of this valence electron, right? So there is valence electron. So in band theory, or say in the theory of the metals, right, we are always interested in the valence electron. So I am interested in this 2s1. So my focus is on this one, right? So this is the diatomic, right? For example, you are having lithium 3 atoms, right? You are having Li3. Okay, this is Li2, and this is the diagram of the Li2. And if you have the triatomic lithium, okay, then definitely you will have the 3 energy levels. Bonding molecular orbitals, say this is your anti-bonding and this is your bonding, and in between them you will have the non-bonding. So this is non-bonding molecular orbital NMO, this is anti-bonding, this is anti-bonding molecular orbital, and this one is the BMO bonding molecular orbital. Now suppose you are having lithium 4. So when you have the lithium 4, then according to the molecular orbital theory, you will have 4 such molecular orbitals, right? So these two are the bonding one and the other two are the anti-bonding one when you are having a like 4. Okay. Now similarly, if I increase this number drastically, right? Say for example, I am taking say Li20, right? So 20 times lithium is present here, for example. So how you can draw these diagrams? Now this will be difficult for you to draw the molecular orbital diagram, but some of you may have some artistic view or artistic talent, so they will try to make them all these, right? 20. And when you do this, then you see these molecular orbitals are very close to each other, and now they appear as a band. And it is a well known fact, whenever you have a very large number of the atomic orbitals or the molecular orbitals, then their energy would be very close to each other, and they appear as a continuum, which is known as the quasi-continuous band, right? And this is how we can originate or we can generate the band in the in any metal. But for your example, for your understanding, I am giving a very important thing here. Say you are having 1 cc of the lithium. That means unit volume of the lithium metal you are having 1 cubic centimeter. Then this 1 cc of the lithium will roughly have the 10 raised the power 23 lithium atoms. Okay. See, this is according to the Avogadro's principle. You know, 1 mole of any substance will have the volume of the 1 cc, and 1 cc will have always the number of roughly 10 raised the power 23 atoms or the molecules. More correctly, 6.023 into 10 raised the power 23. This is according to the Avogadro's principle. So if you take the 1 cc of the lithium, that means you have this much of 10 raised the power 23 of the lithium atoms, and definitely then you will have 10 raised the power 23 of 2s orbital. And now you have to draw these molecular orbital diagram for 10 raised the power 23 such 2s molecular orbital, then definitely this will produce a band. So this is how we can generate the band in the band theory of the solids. Now if you want to check more clearly how we can draw it, so now I am going to discuss how we can do this. Energy level first. Say this is the energy which is going up. There is no problem in that. And as I already told you, for example, see I am interested in the lithium atom, so I am discussing that lithium only. Say this is your lithium. Atomic number is 3 and it is having 1s2 and say it is 2s1. So in the light of the molecular orbital theory, what we can do, we can write, say this is 1s of the lithium atom, and this 1s of the lithium atom is having 2 electrons, as you can see here in the electronic configuration. So you can straightforward put 2 electrons in this 1s orbital, right? And similarly, say you are having this very large number of the lithium atoms, so definitely you will have very large value of n1s orbitals, and then you can write or you can draw this as well. This is another 1s orbital, and don't forget this n is roughly 10 to the power 23 according to the Avogadro's principle, right? So what you can do here, now now you can understand, when these much number of this very high number of the atomic orbitals of 1s are combining, so they will produce this much number of your molecular orbital, and their energy would be very close to each other, and they appear as a band. So how we can draw that band? So this is the band. This is actually the band, right? And you know, since this is complete, this atomic orbital is completely filled, so this band is also completely filled with the electrons. All electrons are there, and if you want to see how actually the arrangement of these orbitals or the electrons are there in it, then you will find quite a large number of closely spaced orbitals in this. Very large number of closely spaced orbitals into this. Okay, and they appear as a band, which is known, they appear as a continuum, and that continuum is known as a quasi continuous band. Basically this term comes from the uh, uh, quantum mechanical treatment. It is very, very important. Okay, and whatever the electrons are there in it, they all are delocalized into entire in this entire band, right? They are not belonging to one particular molecular orbital, but they are moving freely on these orbitals. They are completely delocalized. This is how we can produce the band here. I hope this is quite clear to you, but I am interested in your 2s orbital. So what I am doing here, say I am making this 2s orbital of the lithium, and definitely it will have only one electron, since in the electronic configuration you can see in the 2s orbital you are having only one electron. This is quite obvious, right? And then you are having very high number of these things, which is n here. Again I am writing 10 to the power 23 of n such 2s orbital which are having only one electron, and then you are having another one of 2s, right? And then you can produce your another band. How we can produce this band here? So again I am going in that manner, drawing in that manner. Okay, just like that. Fine. I am taking little bit of time in drawing this. Make that. And like that. Okay. So this is what this is the 2s band. And you know, this atomic orbital of 2s is having only one electron. That means whatever the molecular orbitals are there in it, only half of them would be filled, because atomic orbitals already are half filled, right? So band will also have only half of the electrons. So it is 1 by 2 occupied only. How much? 1 by 2 occupied only. That means half occupied. When it is half occupied, so what you can do, you can draw like that, you can draw. Okay, so this is your second band. But you know, above this you will also have 2p orbitals, right? This is how we can draw it, right? So now first of all we need to understand what is happening here. Okay, so for this you need to know this is the this is your quasi continuous band. This is as well your quasi continuous band. They all are the bands actually. Okay, and you can see here in this region, basically this region, see, you know, this is the 1s of that, or 1s of the lithium. This is 2s of the lithium. This belongs to the second shell. That means the principal quantum number is 2, and here the principal quantum number is 1. And in the light of the Bohr theory, you know, there is a significant energy gap between energy difference between the principal quantum number 1 and principal quantum number 2. That means there is energy gap between the two. So this we can call it as the forbidden energy gap, right? This we can call it as forbidden energy gap. Forbidden, that will not allowed energy gap. I hope there is no problem in that, right? And then you can go a little bit further. See this I have already explained you, but I am not interested in this because they are not involved in the conduction, whether in the thermal conduction or in the metallic conductions. They are not very much responsible. Okay, but if you go for your 2s, right? This 2s is half filled. This is now half filled. You can see here. And when this is the lower half, which is the filled one, and this is the upper half, which is the empty one, right? This is quite clear. Okay, that means if you supply, see, in case of the metals, generally what happens, if you keep this lithium at the room temperature, so at the room temperature sufficient energy is available for these electrons, and they can move from this this filled half to the empty half, right? So there is natural conductions in the metal, whether it is the lithium, sodium, potassium, or any other metal. So the sufficient amount of energy is available at the room temperature, and these electrons are free to move here and there. And you know, when electrons are moving from one position to position, that means they can conduct the electricity, right? Whether it is a thermal or the electrical conductivity. I hope this is quite clear to you. Now you can go for the 2p orbitals, right? So in the 2p orbitals, you know, 1, 2 and 3 and 3, 6, and these two are 8. So total of 8 orbitals are available, and only one electron is there to fill in this 8 orbitals. So that means this is a, if you check this entire one, right? If you check this entire one, so there is only 1 by 8th filled. There is only 1 by 8th filled. This is something very, very important you need to understand, because only one electron is there. So it is, and 8 orbitals are there. So it is 1 by 8 filled. It is very, very important to understand. Okay. Now you can see here this 2s band and the 2p bands, right? This area is basically the overlapping zone, right? This is your overlapping zone. Basically this zone, you know, this if you see this zone actually, right? This zone contains how many electrons? Only n electrons, because n such atoms are there, and it is only 1 by 8th filled, and as I already told you, right? So promotion can take place from here to here as well. This is something very, very important. So it's these things you need to understand. But you cannot promote the electron from this band to this band, right? Because this energy gap is quite high, right? This energy gap is that much of high. If you try to give the very high of energy to this, then your metal will melt or the decompose. But the promotion of the electron will not be possible in that case, right? And remember one thing: the zones where the electrons can move are called the permitted zones. So in your textbook, you can find various things here. So first of all, I am writing permitted zones. Permitted zones. So what are the permitted zones? The zones where the electrons can move, right? Where the electrons can move. So I am writing zones where the electrons can move, right? So now you can see here, these electrons can change their positions. They can come here, these can go down. So they are also the permitted zones. This is also the permitted zone. Electron can move from here to there, but this is not the permitted zone. Basically, this is no energy zone, and here you will not find any electron. This is something very, very important. Okay, that's why it is known as the forbidden energy gap. And this gap you can call it as the forbidden zone. Sometimes it is also known as the forbidden zone. So I am writing it as forbidden zone as well. Forbidden zone. This is quite important. Okay. So these things are very, very important. I hope this is quite clear to you. And see, there are various technical terms for these orbitals, right, or these bands, right? But I am not going to discuss those things in the pretty much detail here, because I am discussing for the chemistry people only, not for the electronics or the physics peoples, right? But sometimes you may find different kinds of the terminology in that case. Say for example, sometimes in some textbook you can also find this term, Brillouin zones, Brillouin. So it is enough for the chemistry people to know the meaning or the definition of these, right? So basically, Brillouin zones are what? They are the permitted energy levels. So basically, you can call it as the permitted zones, right, or the Brillouin zones. Okay. Then there comes the Fermi level. Another very important term is the Fermi level. So what is Fermi level? Fermi level is a level below which all the bands are filled, right? So this is again very, very important term. So I am writing here. So these terms are very important, and you need to understand these terms. Now based on this, right, this energy gap, right, and this overlapping jet, that basically based on this band theory, we can describe the nature of the material as conductors, insulators, as well as the semiconductors, right? So, say for example, right, this one. First of all, you see both diagrams are same, right? Both these diagrams are same, okay? And see, you can see here this level, right? This green one is the filled. This is the filled area. Green one, electrons are there. Again, you can see the electrons are there. Electrons are there, and there would be energy level, which is known as what? Fermi level. As I already told you, below Fermi level, all bands are filled, right? So this is the Fermi level, and you can see if you go here, then Fermi level will go just like that here. Say this is the filled one, valence band. This is again the valence band filled one. This is again the valence band filled one, and the above one is the conduction band. So basically, if you go back, right? If I go back, please remember this 1s band is normally known as the non-conduction band, because core electrons are not involved in any kind of the conduction, so it is known as the non-conduction band. But the upper one is the conduction band. Upper one is the conduction band. However, they all are technically known as the valence band, as I already told you, right? So here I have explained you all the things here. Now you see this one. So what happens in case of the metals and the non-metals and the metals, conductors, semiconductors, and your insulators. Say this is the example of your metals, right? Say here metal is given here, and this is the band. Okay, this is the valence band, and this is the conduction band, and this is the overlapping area which is generally there in case of the metal. Whether you take the example of the lithium, which I have only taken here, whether you take the example of the sodium or any other metal, you will always find this overlapping zone. And this energy gap is very, very low. At the room temperature, sufficient energy is available for the electrons to move from this valence band to the overlapping zone, as well as to the conduction band or the conduction zone. This gives the very high conductivity to the metal, whether it is the electrical conductivity or the metallic conductivity. Please remember that in this case it is very, very small, right? But if you go for the insulators, you know, the insulators are those materials which cannot conduct the electricity, or which cannot show any kind of the conductivity, whether thermal or the electrical conductivity. What is the reason is that? Because in that case there is no overlapping zone, and the energy gap between the valence band and conduction band is very, very high. We cannot promote the electron from the valence band to the conduction band by supplying any amount of the energy, because higher energy can change the state or may even decompose your metal, but the promotion would not be possible in that case, right? So technically, if you go for the quantitatively, what is the magnitude actually? So please remember, in case of the insulators, I am writing here insulators. I am writing insulators. Okay. So in case of the insulators, this energy gap is very, very high, roughly greater than 5 electron volt. You can very easily convert this electron volt into the joules or in the kilocalories like that, but I am not going to do those conversions here actually. If you want to know how to convert it, I have already made a video for this conversion. I'll give you the link in the description box for this conversion if someone wants to know how we can do that. So he or she can go through that particular lecture. So this is very high energy, right? But in case of the semiconductors, right? In case of the semiconductors, this gap is quite low. So in case of the semiconductors, what I can do, I can write here, this gap in case of the semiconductor is basically less than 1 electron volt. When it is 1 electron less than 1 electron volt, that means if you supply that means they can conduct the electricity, or they can show the conductivity, whether electrical conductivity or the thermal conductivity. This is something very, very important to note that. But see, this matter is quite clear now. And your insulators are quite clear now. Here you can see in case of the insulators very large gap. In case of the semiconductor, this is quite low, less than 1 electron volt. Here greater than 5 electron volt. Here there is no such gap, right? In case of the conductors. But you know, these semiconductors are quite different type, and semiconductors you can classify in the two ways, right? First of all, your intrinsic semiconductors. Intrinsic semiconductors, and next one is the extrinsic. Okay, so intrinsic का मतलब that is they are 100% pure, or extrinsic are what? They are doped. And what is doping? Doping means addition of a small amount of the impurities to anything. That is called the doping, right? So if you want to know, I can move further. Say you are having this family: carbon, silicon, germanium, selenium, and others, right? Carbon is 6, silicon is 14, and germanium is 32. If you go after carbon, you will find your nitrogen, which is 7 definitely, and after nitrogen you will have your phosphorus, this would be 15, and after germanium you will find your arsenic, I think it would be your 33, and if you go you're from 6 to 5, that means your boron will have the atomic number of 5, and then your aluminium will have the atomic number of 13, and then you are having your gallium. Gallium is 31. Okay, so here you can see this section, guys, this section, right? So not this actually, we can focus only on these two, silicon and germanium. These are the very famous examples of intrinsic semiconductors. Intrinsic semiconductor. Now what we can do, we can generate the p-type and n-type of the semiconductors, right? So say for example, now say I am discussing here I am discussing p-type semiconduction or p-type semiconductors. P-type semiconductors. How we can produce p-type of semiconductors? Okay, first of all, you take any of these two, whether you can take your silicon or you can take your germanium. So for simplicity, I am taking the example of the silicon. Yeah, this is the silicon having the atomic number of the 14, that will 2, 8, and 4. Clear? And now what I am doing here, see, the first instant what I am doing to this silicon, I am adding the impurity of the little of the aluminium. So I am adding little of the aluminium to the silicon. So the moment I add aluminium to it, aluminium is having atomic number of 13. If you write the configuration 2, 8, and 3, right? So this is the configuration. Now this system is the doped system. It is doped. Again it will behave as the semiconductor, but hey, this semiconductor would be of p-type semiconductor. Why p-type semiconductor? You can focus on these 4 electrons, valence electrons 4. Here the valence electron of the electrons of aluminium is 3. So if you add both of these two, this will give you 4 plus 7, 8. 8 electrons are there. And you know, octet requires how many of electrons? That means 8 electrons. So if you subtract 7 from the 8, you will get the 1. That means 1 electron deficiency is there. Deficiency of 1 electron. So I am writing deficiency of 1 electron, then octet. And you know that deficiency of the electron was always present or will always show by the positive charge, which you call it as the hole. And this hole is responsible. This hole is responsible for the conduction, right, in the semiconductors. So such systems are called p-type semiconductors. So for p-type semiconductors, you know, you can understand in that way. You can make a rule of thumb, right? You have this carbon group metal, right? and if you add the group 13 to it, right, say this one, aluminum to this, right, then you will always produce your semi type of p type of the semiconductors, right. If you add little of gallium to the silicon, right, again the same thing will happen. If you add little of aluminium to the germanium, same thing will happen. If you add gallium to the silicon, then again the same p type of semiconduction would be there, right. So this is one example, but a second example can be your silicon and your silicon and gallium, second example. Third example, then you can take your germanium, then germanium and aluminium, and germanium and gallium. These systems will make, right, your p-type semiconductors. Okay. Now I can explain n-type of semiconduction. Where n stands for the, see here p stands for the positive, right, which is the old. N-type semiconductors means where n stands for the negative, and you know the negative is what? Electron. N-type semiconduction. Now for the n-type semiconduction, what I can do? I can add little of phosphorus, right? Little of phosphorus to the silicon. So again, I can write in that manner. This is my silicon, 14. This is 2, 8 and 4, right? And then I am adding little of phosphorus to it. I am adding phosphorus, guys. This is 15. So it is 2, 8 and 5. Now again focus on this 4 and focus on this 5. If you add 5 plus 4, this will give you 9. And you know for octet, you need only 8 electrons. So here 9 minus 8 equals to 1. This is 1 extra electron. This is 1 extra electron. That means negative charge. When now in that case, when you mix this phosphorus to the silicon, you end up with the n type of the semiconductors, the doped one. So one combination is what? Silicon or phosphorus. Another combination can be silicon or arsenic. Then germanium and phosphorus can have another combination. Then germanium and arsenic can have another combination for the n type of the semiconduction. This is very, very important. Now actually what happens when you add the impurity to the system? This we need to understand. Okay, this is something very, very important which you need to understand. Say, let us go back. So here we can see how it is actually happening. So this is we are introducing the pure one. I am not interested in this one, but this is your n-type semiconduction, right? So what happens actually when you make the n-type semiconductors? See, if I go back in the n-type semiconductors, you have added your phosphorus to the silicon. So what happens actually when you add the phosphorus to the silicon? So this actually the energy levels of the physical, what the phosphorus, what actually they will do actually. So this addition of the impurities basically, right, contributes the electronic energy levels, right, and at these electronic energy levels you can see here in the n-type semiconductors, they are very near to the conduction band. This is something very, very important you need to understand, right? So this is the energy gap, right, and near the conduction band in the n-type semiconduction you are having the extra electronic energy levels, right, and these electronic energy levels actually are just above your Fermi levels, right? So this is the Fermi level, they are above the Fermi level. This is something very, very important. Okay, so this shifts the effective Fermi level. What will happen actually to the Fermi level? So when this happens actually, the Fermi levels are shift to a point about halfway between the donor levels and the conduction band, right? So this is the donor level, this is the conduction band, this will shift come somewhere here actually. However, there is if you don't want to understand what happens to the Fermi levels, you can skip that point, but you need to understand in the any n type of the semiconductors, your electronic energy levels are added near to the conduction band, right? So here conduction will occur. But what happens in the p type of the semiconduction? In the p type of the when you add here, see, if I go back here, in the p type of semiconductors, basically you are creating the holes, which I have written here. Okay, so here these actually holes actually are near to the your valence band, actually near to the valence band. It is very, very important, right? The addition of acceptor, this is basically the accept. This is donor impurity, so this will donate electron from this to this. And this is acceptor impurity, this will accept electron from air to air, and then the energy band gap decreases, and then they can go from here to here. So this is something very, very important. The addition of the acceptance impurities contributes whole levels low, very in the very near to the valence band, right, or in the semiconductors. So electron can easily be excited from here to here and then from here to here. This gives the conduction, right? So this is how you explain the behaviors of the semiconductors, conductors, and your say insulators based on the band theory, right? So I hope you understood the thing perfectly. This is the molecular orbital theory of the metals or the quantum mechanical treatment of the bond, right? I hope you like the lecture. If you like the lecture, please hit the like button and do share with your friends as well. And if you are new here watching video for the first time, please subscribe Tetrahedron Chemistry classes. I'll meet you in the next class with certain other topic, right? That's it for today. Thank you very much.